Okay, thank you. Um, Moving right along to the next talk. So this is using power to form solar and storage sizing from Argonne National Laboratory. So on to the next talk.
Hi, thank you. It looks like my picture's not showing up, but hopefully you're able to hear me. I'm Ralph Muhleisen. I lead the buildings group at Argonne National Lab. And I need to thank the power group for the data that they've been creating. You can go ahead to next slide here. I don't have many fancy graphics. Actually, I don't have any graphics because I wasn't sure. I haven't participated in this before, but the project and how we're using the power is very similar to the Dead Day talk that Davis gave earlier. We're using 20 years of location-specific continuous hourly data here. So for including solar radiation, in particular to size PV and energy storage together for the purposes of decarbonizing primary power and or designing and developing backup power in case of outages during extreme events. You can go to the next slide. So one of the things here is I guess the starting point of this is when you're doing solar and storage, you can, as Davis has explained, if you have a certain load that you're trying to meet, whether it's for generation or and possible variation in the solar output, or in the case of backup, when you have no other source of electricity, you can often meet that load by increasing the size of the solar or increasing the size of the storage. And they have different costs. And you have to think about things like, well, it's dark at night. So okay, we have 12 hours or 6 hours or 18 hours, depending on time of year and place that we're at, or 24 hours in some locations when we don't have any potential for sun. Then we have to be thinking here about possibilities of cloudy days, of really cloudy days, of snow that's going on for 3 days straight, and there's like no solar whatsoever going on. So the idea here is we go ahead and look at 20 years of data that comes from the power files, continuous hourly data, to develop a statistical database of the power generation, probable power generation over windows of maybe a day, over 3 days, over 5 days, over 7 days. That tells us how much solar we would be able to get out to provide energy. And then we can use a combination of sizing solar at a cost and sizing the storage at a different cost to optimize the problem for whoever we're working on this. A very interesting thing is that you're able to provide data with the reanalysis data that helps us fill in some of the gaps where there may be only part of the met data. We use primarily solar data, but we also use temperature, humidity, wind. That all goes into much of the generation. And the fact that some of your products here actually cover things like the South Pole are really important. We help to use this in doing a feasibility study for decarbonizing the South Pole, where we have wind and solar that are going together with storage to try to reduce the amount of diesel fuel that you might use or have to use in any way, shape, or form. Our primary use right now, though, is actually this decarbonization planning for backup power for various armed forces, where much of what the fellow from RWI said, you want to have consistent method of working on your tools for doing this prediction and doing the statistics, but you have locations all over the globe. You can go to the next slide. So the fact that your power products have a combination of solar radiation data and met variables like temperature, humidity, and wind, it's really important for getting our estimates of power generation. But the big thing, I think one of the biggest things here is because of the reanalysis that's done in depending upon which product you pull out, the fact that you have glitch-free, continuous hourly data lets us do this statistical analysis. So I can go ahead and develop a solution that says, what's the 99.5% chance that I'm going to be able to power through this outage of 7 days at this military base with a given size of solar and given size of storage given a load? That's the sort of numbers that they want to know. They don't want to know, well, okay, 50% chance using a TMY data, maybe I used an extreme year, but that still didn't include the 7 most cloudy days that could have happened. The second thing is when you're looking here at larger footprints and you're looking at maybe a utility and solar power generation over a utility scale, or an independent system operator, a whole ISO scale, you need to have time coherent hourly data. Because when data is coming from different data sets and different, if you try to use actual data, the fact that it's not time coherent, the reanalysis recreates things on exactly the same time scale. So we can look at the variation, the spatial variation in the output of solar, and know that the time synchronization of those outputs in the wind are really there. So that's how we're using power data. Thank you very much for the chance to talk about it. And thank you all for the product you're creating.